Hello and welcome to today's session. We are going to discuss or extend the discussion beyond what we have discussed yesterday about logistic regression. As the name itself suggests, we are going to analyze the attribute data. So whenever you have your outcome variable, which is attribute data, we end up using logistic regression. We have discussed that there are multiple techniques involved. One is logistic regression, another thing is Logit analysis, and we have Probit analysis. Three things, right? Logistic regression model predicts the probability associated with each dependent variable category. So X is called as dependent variable. X might have binary category or multiple categories for that case. If you have binary categories such as true or false, whether a person is going to default the loan, yes or no, should you approve a credit card transaction, yes or no, is a person going to leave your company, yes or no, will a customer move from Airtel to Vodafone, yes or no, right? All these things are binary. Instead of binary, you can also have multiple categories such as satisfied, neutral, dissatisfied. You can have in this way also, right? If you have multiple levels within this factor x, you call that as multinomial logistic regression. You can perform multiple logistic regression basically, right? So all these are the possible scenarios actually. Yep. So with this understanding, I think we can continue. And these are a few things which we have already discussed yesterday, and it'll be serving as a recap for you all. All right. How does it work? Logistic regression. It finds a linear relationship between independent variables and a link function. Yesterday we have also seen few of the link functions, right? So if it was linear regression, it would have shown you in this way. However, here you have few values which are less than 0. I mean, even so what we are doing here is, if we have discrete or attribute data, which is your y, if your y is attribute, we are trying to plot or we are trying to do a linear regression, right? If we do a linear regression, then this is the outcome which we are seeing, that the probability is below 0. Can the probability ever be 0? Can the probability ever be 0? What is the range of probability? Probability varies from 0 until 1. My question is, can the probability be less than 0? No. What is that, Monica? I didn't get you. Yeah, probability can be 0. Yeah, but it will never be a negative value. Negative probability does not exist. So if you use your linear regression, that is a challenge that you're going to encounter. Hence, if we have attribute data, if your y or outcome variable is attribute data, we end up using logistic regression curve. And this curve looks like an S, and it's called a sigmoid curve. Sigmoid. All right. So we'll take this discussion further. Within logistic regression, you have two things. One is simple, another thing is multiple. If you have a single independent variable model, it is called a simple logistic regression. If you have multiple independent variables such as x1, x2, x3, so on and so forth, it is called as multiple logistic regression. Let us discuss about multiple logistic regression model. Multiple logistic regression model is quite similar to your multiple linear regression model, only beta coefficients vary. So these coefficients what you see here are going to vary in your multiple logistic regression. But this example, this equation here given is about your multiple linear regression model. Now, what in case of logistic regression? As I've told you, you cannot predict a particular number. That's not the objective of logistic regression. The objective of logistic regression is to measure the probability, right? And this is the equation which we have discussed yesterday. Probability is equal to e raised to the power y divided by 1 plus e raised to the power y. And e is a real number constant, which is 2.7183. And y is a response value for an observation. Okay. Now, these are the things which we have discussed yesterday. It's just a recap, right? So there are three methods of logistic regression: binary, nominal, and ordinal. Within binary logistic regression, you'll have binary response variables, two categories: presence or absence of disease, pass or fail, defective or non-defective products, things like that. When it comes to nominal logistic regression, it is performed on nominal variables. These are once again categorical variables that have three or more possible categories with no natural ordering. A few of the people might say food is crunchy, a few might say it's mushy or crispy, right? There is no set order that crunchy should come first, then mushy or mushy, however you want to pronounce. And the third thing is crispy. There's no set order in this way. And if you do not have any natural ordering, then that falls under nominal logistic regression. That's nominal data for that case. And then we have ordinal logistic regression. When the order of your categorical variables is important and when it has a natural ordering, such as strongly disagree, disagree, neutral, agree, strongly disagree, this is set in an order. It will have a sequence. Hence, it's called as order or ordinal logistic regression. These are a few of the assumptions which we have already discussed yesterday, and these are the steps involved in logistic regression. We have discussed all that yesterday. Let us crack this using a simple example. Imagine that you are a data scientist at a very large scale integration circuit manufacturing company. You want to know whether or not the time spent inspecting each product. So how much time are you spending in inspecting each product? Does it really impact the quality assurance department's ability to detect a defect or error in the circuit? Can someone say what is my Y and what is X here? By reading these full lines. Can someone say what is Y and what is X? Y is the ability to detect an error and X is inspection time. That's absolutely right. So you're saying that Y is ability to detect an error. So what could the possible levels be within this Y? Either you detect an error or you do not detect an error. These are the two possible outcomes in this case study. These are the two outcomes, right? Either you detect an error or you do not detect an error by spending some time inspecting a circuit. What do you do as part of your step one? You collect and organize the sample data. How many observations do you want? Error identification process and inspection time, all those are done as part of your step one. Number of observations. You have 55 observations of circuits with errors, and you want to determine whether those errors were detected by QA or not. So there we go. So you have 55 observations that you have taken, 1 until 55, and you have the inspection time, which is your input. How many minutes have you spent inspecting a particular circuit or a product? And if you detect an error, it's classified using yes, 1, right? If error is not detected, then it is 0, 1 and 0. Okay? If you formulate your logistic regression equation, if you use any of your statistical tools, right, you're going to get logistic regression equation. However, this is not a final outcome, right? This is not at all a final outcome. This is just an intermediate step, right? This is an intermediate step to get a job done. That's it. So do not ever assume that this is your final equation, right? You're just there. You have just derived an equation. That's it. Now we need to check whether the model is valid or not. How do you do that? There are two techniques to check whether your model that you have built is valid or not. You can either perform hypothesis testing or you can create logistic regression tables. For hypothesis testing, you can do a test and check whether your p-value is less than or greater than 0.05, right, or alpha value. Okay, or you can create a logistic regression table and actually look into that. How does your logistic regression table look like? Your logistic regression table shows the estimated coefficients, standard errors of coefficients, z-values, and p-values. So let us evaluate or try to spend some time on the table. By the way, any of your statistical tool will perform all these things at one go. You'll get this kind of an output, right? So this is called as your beta naught, and this is called as your beta 1. And you have the associated standard error. Less the error, better it is for you. We have the z-value. We have looked into the z-value, I believe, in the first, second, or third session, right? And you have the corresponding p-value. Here, p-value is less than your alpha value, which is 0.05. This indicates that the coefficients or this coefficient is not 0. And it says that there is a significant relationship between your y and your x. Your p-value says so. And you know that the alpha value is 0.05. It's generally 0.05. Okay. Then you have something called as goodness of fit test using PSN method. Here also you need to look into p-value. Here the p-value indicates p-value is greater than alpha, by the way, or it's greater than 0.05, which is the alpha value. Here the p-value indicates that there is insufficient evidence to reject the null hypothesis. So what would you do? You would accept your null hypothesis. That means that the model fits the data adequately. Now, as I've told you, this is not your final conclusion. This equation is not your final result, as in linear regression, right? This is your final outcome. You have this probability equation and you have your logistic regression equation. Now I just calculate y. In order to calculate y, I use that first equation. Once I get to know y, will be nothing but e raised to the power y divided by 1 plus e raised to the power y. And this is going to give you a probability value. What does this mean? Here, what did I take x as? 40 minutes, right? So what does that mean? There's a 96.11% probability that error will be detected if the QA team spends 40 minutes of inspection during an observation. So on similar lines, you come up with the probabilities associated with each and every value. So each and every inspection time, you're going to come up with appropriate probabilities, right? If you spend very less amount of time on inspection, your probabilities associated also would be very less. And slowly it's going to increase, right? Rapidly it's going to increase. And after a certain amount of time, no matter how much time you spend on inspection, the probability of detecting the errors would still remain the same, right? Okay, sorry about that. That's a train noise. Okay, so hope this is clear. No matter, see, only after you keep spending some significant time on your inspection, your probability of detecting a defect would increase. And towards the peak, no matter how much more time you spend, the chances of you detecting a defect would still remain the same. That is what your sigmoid curve says, or any natural occurring thing. Say your salary is very less. Until certain time, your probability of purchasing a home would be less, significantly less. Most of the people who purchase home would be the people who draw middle income here, right? People who draw moderate incomes would most likely be interested in purchasing home. Your middle class people mostly. People who earn very less. Think about your daily wage laborers, right? They do not ever assume that they can purchase home, or they do not even plan for that, right? Only if your salary crosses a particular value, you tend to think on those lines. Think about the filthy rich people, pink rich. So if a person's salary is 1 crore per annum, if it increases by another 20 lakhs, this 20 lakhs will not necessarily drive his intention of purchasing a house, right? Small delta increase is not going to help. Hence, your probability would start to remain the same, become slightly stagnant. And now, as part of your step 5, you're going to compile the results for each and every inspection time and the associated probabilities. And this example deals with simple logistic regression model, wherein you have uh, X and then probability associated with that. And the same rule applies even if you have multiple logistic regression. You just expand it to multiple values. That's it. Okay, any doubts until here? Any doubts until here? Anyone? Nope. All right. So let us expand our discussion to something called as logit model. Right. So in dealing with attribute data, when you want to estimate the likelihood that an event will take place, we can use tools such as Logit and Probit analysis, which helps to explain the past and predict the future. So here, the thin line of difference between Logit and Probit analysis is that your Probit analysis, which is used using your green, that is going to approach your axis, right? Your axis, this side, it's touching the line very soon. It won't touch, it will go until infinity, but still. So it approaches the axis very fast here and here. However, if you look at your logit analysis, it's not going to touch your axis rapidly, right? That is how it's represented. Then you have your logit and probit analysis. You have your dependent variable, which is y, and you have the corresponding independent variables. You have your x1, x2, x3, so on and so forth. Right? So your logit and probit analysis helps to estimate the maximum likelihood of an event occurrence or non-occurrence. Is an event going to occur or not? Will there be a defect or not? Right? So it estimates the maximum likelihood by predicting an attribute dependent variable, which is your y, from one or more independent variables. So model is going to use y and x in order to estimate the maximum likelihood that an event is going to occur or not occur. It's basically the same thing, but the variant, that's it. Okay. Take this example of vehicle purchase. You could use Logit or Probit analysis if you want to model the effect of consumer characteristics on the type of vehicle purchase. For example, what type of customer buys a sports utility vehicle, van or car, or light pickup truck or motorcycle? For this kind of a case study, you can use Logit or Probit analysis. Logit and Probit assumptions, right? Assumptions are extremely important. You need to remember those. Observations on Y. What do you mean by observations on Y? I have the mean Y, and then I have this dependent variable Y. Within that, I have multiple observations, which is Y1, Y2, Y3, Y4, so on and so forth, right? These are all your observations. Observations on Y have been randomly sampled from the population. Say a population, you're randomly choosing them, kind of, right? Dependent variable Y is caused by independent variable X. So you should have that cause relationship. Remember, not correlation. And remember one more thing which we have discussed, correlation does not guarantee causation. And here we are not discussing about causation, right? We are discussing, here we're not discussing about correlation, we're discussing about causation. So X should cause Y. Relationship between Y and X is uncertain. You do not know what is the kind of relationship which we have. You know for a fact that there is a relationship, but you do not know to what extent and how the relationship exists. And you have to also assess the distribution of your error terms. What is the distribution that your error terms follow? And I'm pretty sure you all know what an error and what a residual means. These are two the same names. Wherever there is a causation, you can use logistic regression, provided the other assumptions also hold true. That is, you need to have Y, which is attribute data and all that. All right. So what is the main difference between these two? What is the main difference between Logit? So your Logit model has slightly flatter tails. Here, Logit, slightly flat, right? And the normal or Probit curve approaches the axis more quickly. So here you see that your Probit curve is approaching the axis faster. Although both of these deal with population parameters, the estimates might differ because both of these, Logit and Probit, have different purpose and methodologies. Here we have the characteristics of Logit analysis. So Logit analysis, right, produces results that are statistically sound. It helps you avoid out-of-range estimates by transforming a dichotomous dependent variable into a continuous variable. So you have your y, which is your dependent variable. Now we have yes or no kind of y, right? That is called as dichotomous. Dichotomous means pros and cons, two things basically. Dichotomous. So y has yes or no kind of a thing, male or a female, will there be a defect or not, will a person purchase or not, right? So that kind of data is transformed to a continuous variable. How do you transform that to continuous variable? By taking the probabilities basically. You have this, it ranges from minus infinity here somewhere until you're plus infinity. Logit analysis results are easily interpreted. You did not get that. What you did not get, Aditya, here? You have your whether, okay. So take example of the defect. Will you get a defect or not? That is your y, right? In an earlier example that we have seen, y can be defect or not. How many outcomes do you have? How many outcomes do you have if I say two outcomes? How do I make it infinite? How do I make it infinite? In this way, right? So probabilities range from what to what, 0 until 1, right? Yeah, so you can have 0, you can have 0.01, you can have 0.0.2, you can have 0.3, 0.4, 0.00006. So you're getting me? It's taking that entire range. So it's transforming that into your continuous data. Okay. Uh, I mean, there are a few more things which we are going to learn, right? Which will say that you're going to transform this, the values to minus infinity to plus infinity. I'll just explain you about that. So characteristics of Logit analysis. Logit analysis allows you to apply the analog analog of the regression t-test by giving parameters. So all that is fine. Let us look into the example. Don't worry about this explanation. It will become clear as and how we progress further. Analog, the digital and all that, right? So a marketing company might use Logit analysis to test brand preference and loyalty for a certain product. So it uses something called as odds. You might have heard about this, right? There are odds are in my favor, odds are against me. People keep using this kind of an English statement in their general conversations. Odds are in my favor, odds are against me, and things like that. So that is the same logic which is applied here also. It uses the odds to determine how much more likely it is that an observation will be a member of one category instead of another. Right? Let us understand this. What exactly does this mean? If I say a probability of P is equal to 0.8 of being in group A, if I make that statement here, there's a probability of 0.8 of a particular member falling in pass category or fail category, for example. Okay, if I say that this is group A and this is group B, then if I say that there is a probability of 0.8 or 80% of falling in this group, probability of any student whom you pick is going to fall in this group A, which is nothing but pass. This can also, or probability of 0.8 can also expressed in odd terms using this 4:1. What does this mean? There are 4 chances to pass for a person to fall into this category called pass versus only 1% chance or only 1 chance that your student or that the student whom you picked is going to fall in this group B. What does 80% mean? 80% out of 100% would be 4 parts, right? Probability would always be 0 to 1, which is 0% to 100%. If I'm saying probability is 0.8, which is 80%, 80% is 4 parts of 100, right? So 100 can be represented as what? 20% plus 20% plus 20% plus 20% plus 20%, right? So if we can have 5 20% and sum those, it would translate to 100%. When I say probability of 0.8 or 80%, then that means I'm considering all these 4. All those 4 things. Right? Hence you call it as 4 parts. And you have 1 part here. So 4:1. Is this clear? Okay. Then you have the Logit formula here. Where is my pointer? Okay. Logit is equal to nothing but log of P divided by 1 minus P. And we know for a fact that the logit ranges from 0 until 1. And hence your L value would lie between 0 and 1. And the probability of any given one value, for a given L value is provided using this equation. P is equal to e raised to the power L divided by 1 plus e raised to the power L. Okay. After knowing the P value, we can actually calculate the odds. Odds are in my favor or against my favor, things like that, right? You can arrive. Absolutely. Logit analysis and logistic mean the same, right? In most cases than one, it's the same. But again, we have been discussing logistic regression separately and logit separately for a reason. But otherwise, I would say it's the same. Okay, so imagine this. Imagine the same exercise, logit analysis is what we are performing now. Imagine that you're a data scientist at a very large scale integration circuit manufacturing company. You want to know whether or not time spent is your input variable X, is, right? Amount of time you spend inspecting a product or observation, is that going to result in you detecting an error or not? Yes or no, right? That's your Y. Let us see how to proceed here. How many observations did we take initially? 55 observations, remember? 55 observations. So let me go back and show you that. So we have your 55 observations here, 1 until 55. And how many defects do you have? If you start counting 1 defect, 2, 3, 4, 5, 6, so on and so forth, you'll get 27 defects. So you have 27 defects out of 57 total observations. So that takes the p-value to 0.491. This proportion, right? If I have 27 defects out of 55, what would the proportion of defects be? 49.1% approximately, or 0.491. If I want to calculate the odds, this is how I'm going to calculate. And I'll say that 0.965 is to 1. How do you infer? Or how do you write the inference? I want you guys to write the inference based on this. Can someone draw inference? There is a 0.965, right, chance that you will identify a defect. Right? So we are taking that conversation further here. Now remember that VLSI manufacturing example which I've shown you, and based on that we have calculated 96.11% chance, right, that a person is going to, or a QA department is going to detect a defect if they spend 40 minutes inspecting the product. Again, odds ratio formula is the same, P divided by 1 minus P. You get this. So the results is odds of so much. Odds for detecting the defect, right? Your job is not done yet. We now need to find out the logit. Logit is nothing but log of P by 1 minus P. Here P by 1 minus P is 24.71. If you take a log of that, you get 3.201. Now you calculate the probability. Now e raised to the power L divided by 1 plus e raised to the power L, you'll get 0.9611. All right. So now let me take you back to our initial calculation on how we have got here. Same thing. For the given x value, calculate the y value and substitute in this equation, and you get the probability, 96.11%. Another way of doing that is, first you calculate the odds, which is P of 1 minus P. Calculate the odds. Once you calculate the odds ratio, this is called as odds ratio, you take a log of that to get L. Once you get the L, substitute in this equation. Are you able to get the thin line of difference between these two? There you're using what? Equation, right? Y is equal to mx plus c kind of an equation to get the y value, and you're substituting in the formula, which is nothing but e raised to the power y divided by 1 plus e raised to the power y. To get the probability. And this is another way of dealing with that. You first calculate proportion, you take p by 1 minus p to get a value, It's 24.71 in this case. And then you take the log of that. If you take the log of that, all you will get is the same number, 3.207. You substitute here. Is this clear or do you have any doubts? By the way, log of the odds ratio, uh, one second. Yeah. Log of this odds ratio is called as Logit. That is how you statistically see, right? This is your odds ratio, p by 1 minus p. If you take a log of that, you'll get the Logit. Then we have Probit analysis. Probit analysis, you can consider this as a specialized regression model which is used with binary dependent variables. If your y says 0 or 1, as in the case of defect found or not, you can employ Probit analysis using something called as Probit link function. Now here it's very similar to your Logit analysis, but only thing is it uses cumulative normal probability distribution. And this Probit analysis is preferred when your data are normally distributed. This is a sigmoid curve. In this Probit analysis is going to transform your sigmoid curve to a straight line. And if you have a straight line, you know for a fact that you can either use least squares or maximum likelihood to come up with your outcome. Yesterday we have discussed that it's mostly used in survival analysis, right? Survival analysis is more relevant to your medical industry on how many days after your cancer surgery a patient is going to survive, for example. If I have that kind of an analysis on even after cancer surgery, if people are dying, then I'm going to give that as an option to the patients. Either you can undergo the surgery or you might not want to undergo the surgery. And this is used in the descriptive testing. Here we go. This is the Probit model equation. What is this called as? This notation. Yeah, it's phi basically. Now you have all the notations here. You have to use this to come up with the Probit model equation. For Probit equation also you have again tests, right? You look into goodness of fit and you also look into your probability plot and check whether you're, and here on the fitted line, this is your fitted line, the blue line. Closer are your dots to the line, the better the model fit. And here you can also calculate the table of percentiles with respect to your Probit analysis. What percentage of an event or non-event takes place at what level, basically. So you have 1 to 60 levels. You have the standard error, you have the upper limit and the lower limit associated with each value there. So if you do not understand, forget about that. It's not extremely important. Probit analysis is actually out of scope. I just put it here so that you might want to read that at your own leisure. So simple example, metal manufacturer. Imagine that you're a data scientist at a metal manufacturer. You're validating the product's capability of sustaining stress during transportation. So during transportation, few of the goods break, few of your products are misaligned. So it's as good as delivering the customer a defective product. Hence, you're doing some kind of a test on that. So you conduct number of destructive tests and you collect the samples. You set the pressure machine at various pressure levels and record the braking response in binary data, 0 or 1. All your cars, right? All your vehicles are tested even before they're released in the market for the safety. It goes crashes against the wall and then they check the impact on humans sitting there, to what extent it's going to damage, right? Do you have the safety bags coming out on time and things like that. Even when it comes to the brick, for house construction you have bricks, right? It undergoes this destructive testing to check on, if I put a lot of pressure, what is happening? Is the brick breaking or not? Things like that. So you tested 50 samples with which ranges from 10 to 50 a Newton meter square, I believe. What is the unit for pressure? Newtons, right? So I'm right on that. Okay. So if I apply so much of pressure, this is what is happening. If I apply so much of pressure, they're not failing, right? So 45 failed, 5 did not fail. At pressure level 20, 38 survived, 38 survived, and 12 failed the survivability test. And if I apply pressure of 30 newtons, 30 survived and 20 did not survive, in that sense, right? So again, once you're done with that, you can use any of your statistical tool to calculate the beta naught and your beta 1. How to calculate a beta naught and beta 1? There you go. So you have minus mu by this, beta 1 is 1 by standard deviation. In that way you calculate those values. Once again, goodness of fit test, you use Pearson, right? All you should be interested in is your p-value. If the p-value is less, here the p-value is greater than alpha, right? It's greater than alpha. Alpha value being 0.05. P high, obviously null fly. What does null say? There is no difference between observed and predicted values. So we conclude that the Probit model fits the data well. And if you want to look into probability plot to gauge whether your model is fit or not, you draw a fitted line. This is your fitted line. This blue line, sorry. Um, this blue line. And then how close are the data points to the fitted line? That is going to explain about your model being fit for use or not. Once again, you calculate. For each and everything, you're going to calculate the percentile. This table of percentiles tells you what percentage of an event or not even non-event takes place at what pressure level. For example, at 77.43 Newton per square meter pressure, only 20 cans survive. Here it is. If I put so much of pressure, only 20 cans survive. So you can calculate all this. All right.